Hi, welcome back to General Chemistry 1. Let's talk about bond energy in this video. So bond energy actually is another word called bond enthalpy or bond strength. It determines how strong the bond is. We can use its abbreviation BE to refer a bond energy. It's defined as the standard enthalpy change for breaking the bond in 1 mole of gaseous molecules, and it's always positive. So for example, we have a A-B bond in gas phase, and after the reaction, we have the A in gas phase and B in gas phase, so the bond breaks. And the standard enthalpy change for this bond breaking reaction equals to the binding energy of A and B, and it's always larger than 0. So strong bonds have a larger bonding energy, vice versa. So the larger the bonding energy, the stronger the bond is, and the smaller the bonding energy, the weaker the bond is. In the textbook, table 9.2, it lists many common bonds, chemical bonds, and their bond energies. So one thing to pay attention that the energy of a given bond actually varies slightly from molecule to molecule and sometimes even within the same molecule. So the bond energy in table 9.2 is an average bond energy. For example, the carbon-carbon single bond has a bond energy of 347 kilojoules per mole. And that's the average of all the carbon-carbon single bonds in all of the molecules, all of the compounds there in the world. Okay, so it's just an average bond energy. All right, once we know the bond energy concept, we can have a few ways to determine the bond energy or compare the bond energy between different molecules. One way is to refer to the bond order. When we talk about bond order, we usually talk about covalent bond. For a covalent bond, only valence electrons can participate in a bond formation. And the bond order is the number of electron pairs being shared between the two bonding atoms. Okay, and for a single bond, the bond order is 1. For a double bond, the bond order is 2, and for triple bond, the bond order is 3. So if you don't know about how many pairs of electrons are shared, just look at how many lines are between the two atoms. If there's only one line, it's a single bond, the bond order is 1. If there are 2 lines, it's a double bond, the bond order is 2. So for the same 2 atoms, the atom needs to be same. The higher the bond order, the stronger the bond. So let's take a look at a few examples. If we have the carbon-carbon single bond, double bond, the triple bond, the energy corresponding bond energy actually increases from 300, 600 to 800, and it follows this trend. The higher the bond order, the stronger the bond is. It also applies to nitrogen. Nitrogen single bond, double bond, and triple bond has an increasing bonding energy. And even with the 2 binding atoms that are of different atoms, for the nitrogen-oxygen bond, the single bond, double bond, and triple bond has an increasing of bond order and also has increasing of the energy. So if we are giving you a series of bonds with double, single, double, and triple bond, you should be able to tell, like, the higher the bond order, the stronger the bond is. Okay, besides the bond order, the bond energy can also be associated with the bond length. Okay, bond length is the distance between the nuclei of the 2 bonded atoms. And we can determine the bond energy based on a series of similar bonds that have known bond length. So with that said, we have a few requirements that needs to be met. So for a series of heteronuclear covalent bonds, so first needs to be covalent bonds and the 2 bonding atoms are different. So the requirements are, first, they have the same bond order. We don't want bond order to mess up with the sequence of bond lengths. Okay, so they need to have the same bond order, and 2, share 1 common bonded atom. So that means it can be, say, carbon-oxygen bond, carbon-carbon bond, carbon-hydrogen bond, carbon whatever bond need to have one common bonded atoms. Okay, if a covalence bond meet with these two criteria, then the smaller the bond length, the larger the bond energy or the bond strength. So we can verify these rules in the table 9.2. If we look at the hydrogen halogen bonds, HF, HCl, HBr, and HI, you can see when the length of the bond increases, the energy of the bond decreases. Or in other words, if the length of the bond decreases, the bond energy increases. It can be understood in this way. According to Coulomb's law, when these two atoms are getting closer, which means the bond length is smaller, one atom will feel stronger attractions from the other because of the shorter distance. So the bond energy is larger. It's harder to pull them apart. Yeah. So besides the H halogen bond, we can also take a look at the triple bond. We have carbon-carbon triple bond, carbon-nitrogen triple bond, and carbon-oxygen triple bond. The same trend follows. The smaller the bond length, the higher the bond energy. Okay. And finally, based on the polarity of the bond, we can have a rough estimation of bond energy. It goes like this, a little bit complicated, but pay attention. Given the bond energy of two homonuclear bonds, so it's either carbon-carbon bonds, chlorine-chlorine bonds, oxygen-oxygen bonds, the bonds made by same atoms. It's called the homonuclear bonds. The more polar the heteronuclear bond, the greater the bond energy is above the average of the two homonuclear bonds. Let me explain what that means by giving you an example. Estimate the range of the bond energy of silicon-oxygen bond. And you are given the bond energy of oxygen-oxygen bond, which is 204 kilojoules per mole, and the silicon-silicon bond energy, that is 226 kilojoules per mole. Okay, so now you have two homonuclear bonds, oxygen-oxygen bond and a silicon-silicon bond. So the more polar heteronuclear bond is, so the more polar SiO bond is, so you pick up one atom from each homonuclear bonds and make them a heteronuclear bond. The more polar SiO is, the greater this SiO bond energy is above the average of the two oxygen-oxygen and silicon-silicon bonds. So with that, you may take out a scratch sheet and try to work out this problem by yourself. Okay, so because what we are comparing is the bond energy of the silicon-oxygen bond with the average of the oxygen-oxygen bond and silicon-silicon bond. So first, we need to calculate the average of these oxygen-oxygen and silicon-silicon bonds, the average of the two homonuclear bonds. So the average of these two is 215 kilojoules per mole. Okay, now we need to determine the silicon-oxygen bond, whether it's polar or nonpolar, and how much polarity it is. So for silicon-oxygen, we found the electronegativity. The electronegativity difference is 1.7, so it's quite polar. Then, because it's a polar bond, the bond energy of silicon-oxygen will above the average of the oxygen-oxygen silicon-silicon bond. So the bond energy of silicon-oxygen will be larger than 215 kilojoules per mole, the average of the two homonuclear bonds. Imagine we come up with electronegativity between silicon and oxygen, like very close to zero, which means this bond is almost nonpolar. Then the estimated silicon-oxygen bond will be about, maybe a little bit higher than the 215, the average of the two homonuclear bonds. Yeah. All right, this is the end of this video, and I'll see you next time.